The most typical type of capacitor and the model that we'll use to think of capacitors, most of the time that we do think of capacitors, is what we call a parallel plate capacitor. Okay, so the basic idea here is we have a thin metal plate like this, and I'll draw it kind of in perspective, although we won't always bother with that part. And then parallel to that, I want to have another one just like it. Okay, so two parallel plates, like so. And what we're going to have, just like we saw in the case of the sort of general capacitor, is we're going to have one charged positively and one charged negatively. Okay, so equal and opposite charges plus Q on one plate minus Q on the other. Okay, and if you think about what the electric field will look like in a case like this, well, we know the field lines will start on the positive charges and end on the negative charges, and so essentially the electric field will go directly from one plate to the other. Okay, and in a parallel plate capacitor, the electric field is basically uniform in between the plates. That's one of the things that's really nice about these, that the electric field is uniform. So in a textbook problem, we will often think about, okay, we have this region with a uniform electric field, and then we want to study something that happens in that uniform electric field. And that may seem kind of made up to you, but it turns out it's actually pretty easy to achieve that in real life. We take these two metal plates parallel to each other, put a positive charge on one, negative charge on the other, and just like that, we have essentially a uniform electric field in some region of space. Now, in real life, the field doesn't look quite that uniform. It's only an approximation. So if I take a situation where I have these two plates like this, and I try to draw the electric field here, what typically will actually happen is the field will kind of bow out a little bit, like this. And you'll end up with, maybe some kind of going around like this. Okay, so the field will not be totally uniform in between, but if you consider the spot between the plates, it's still pretty uniform. It's uniform enough to be useful. Okay, so this shape of the field lines we call fringing. Essentially, the field lines will spread out a little bit towards the edge. And so if you want a basically uniform electric field, you want the plates to be pretty close together and pretty large relative to the distance between them. And then you want to use the part that is closest to the middle of the plates. Okay, so that's a more realistic picture, but even for the idealized case, it's a pretty good approximation. Okay, so what can we figure out about the electric field in between the plates? Well, let's consider each of the two plates individually. So let's consider the top plate, like this, which has positive charge. So if I draw electric field vectors, they'll look something kind of like this. We know the electric field is basically constant near a charged sheet, and that's basically what we have. So it'll look something kind of like this. Okay, pointing away in that case. All right, well, let me have then the negative plate over here, which will have negative, negative, negative like that. And this time the field vectors are going to point towards the negative plate. Okay, and that'll be true both above and below. Okay, but the electric fields don't stop at each of the plates. All right, so the negatively charged plate will also have an electric field towards the negatively charged plate way out here. We're assuming that it's basically independent of distance. And the same for the positively charged plate. The electric field will point away from that plate everywhere, like this. And what we see is that if I add together those two fields, if I superpose those in all of the places, I get cancellation here. I had equal and opposite charges on the two plates, and we're assuming the plates are really large compared to the distance between them, so this is kind of just a cartoonish sketch of what's going on, the electric fields will be about equal and they will about cancel out here. The same is true below the other plate. We have equal and opposite electric fields from the two plates. But in between, the electric field doesn't cancel out. In the space in between, we get the electric field is going to add together. So instead of canceling out, we're going to have a big electric field between the plates. All right, how big? Well, we know the electric field from a sheet is equal to sigma over 2 epsilon naught, where the sigma is the charge per area. You derived that before. And here we have two sheets. So that means that where the two electric fields are adding together, they have the same area, they have the same charge. So the electric field inside a capacitor, at least a parallel plate capacitor, is going to be twice that. So sigma over epsilon naught. Okay. Okay, so what I would like to do next is take this electric field that we just calculated and use it to figure out the capacitance in the case of the parallel plate capacitor. Okay, so I'm going to imagine that I take a particle and I move it from here to here, so from one plate to the other, and I want to know for that test charge, what is the delta V? What is the potential difference between those two plates? All right, and so how do we do that? Well, I have a formula for delta V. Delta V is equal to negative the integral of E dot ds. All right, and what we're really interested in here is the magnitude of the difference, so I'm not going to worry about the minus sign too much. But notice that we have the electric field is constant. And it's not only constant, we have a magnitude for it, sigma over epsilon naught. And the path that we're following is parallel to the electric field. Okay, so I've drawn a path from one plate to the other, which goes with the electric field. So that's basically just going to be E times the distance between the plates. Okay, so this distance is D. Okay, and again, I'm ignoring the minus sign because I'm only interested in the magnitudes. Okay, well, what was the formula for capacitance again? Well, the defining relationship is Q equals C delta V. So C is then going to be Q over delta V. All right, and we have an expression for delta V, and we have an expression for Q. Okay, so the delta V is going to be E times D, and Q is Q. And the electric field is sigma over epsilon naught. So Q over sigma over epsilon naught times D. Remember that the charge density, sigma, is equal to Q over A. So I'll plug that in, and then I've got Q over epsilon naught A times D. And I can rearrange that, and I'll get epsilon naught A over D. The charge cancels, and we're left with only things that depend on the shape of the capacitor. Okay, so let me write that out just as the final result. So C for a parallel plate capacitor is epsilon naught A over D. And I think some of the most interesting things here are what does not show up. So it turns out it doesn't matter what material the capacitor is made out of. It doesn't matter if it's copper or aluminum or steel. That doesn't show up anywhere. What does matter is the area of the plates and the distance between them. So we also don't care what the shape of the plates are. It could be rectangles like I drew, or they could be, heart-shaped or any other weird shape. Doesn't matter as long as they are parallel to each other. Okay, and then kind of making sense of this relationship for the parallel plate capacitor, if we increase the area of the plates, then that's going to increase the capacitance. Remember what that means is we get more charge for the same delta V. Okay, If we increase the distance between the plates, then that will decrease the capacitance. We'll get more delta V for the same Q. All right, so the reason that makes sense is the electric field will be the same if the charge is the same, but you'll have a longer distance for the delta V to build up. Remember, the delta V is the electric field times the distance.